Hello and welcome to this screencast recapping the main ideas of section 5.2 of active calculus on the second fundamental theorem of calculus. In some books, if you've seen calculus before, might call this the first fundamental theorem of calculus, or part 1 or part 2. There are two main parts of the fundamental theorem of calculus, and we've already seen the first fundamental theorem of calculus, which we called the fundamental theorem of calculus, or the net change, or the total change theorem, which said that we can use an antiderivative to evaluate a definite integral or to find the net signed area between the graph of a continuous function and the x-axis. So here, we're going to build on the ideas we developed in section 5.1, where we looked at functions that look like this. They're defined in terms of an integral and are sort of saying, tell me the net signed area under the graph of f, or between the graph of the function f and the x-axis on the interval from c to x, where x is a variable. And the second fundamental theorem of calculus says that if f is a continuous function and c is any constant, then f has a unique antiderivative, a, that satisfies a of c is 0. And we can find that antiderivative by integrating f from c to x. And that seems a little surprising on the surface, but if you think back to what we were seeing when we were looking at the graph of an integral function like this and the graph of f in a previous screencast, we were noticing lots of behaviors that suggested that f was the derivative for a. And in fact, if we take a look here, another way of restating the second fundamental theorem of calculus, or part of it, is that the derivative with respect to x of this integral function, right, this is just a of x here, so we're saying dx a of x equals f of x. In other words, a is an antiderivative for the function little f. And that's actually the most common way that we'll wind up using the second fundamental theorem of calculus, is we'll take an integral function and we'll try to investigate it by looking at its derivatives using the second fundamental theorem. The other point the text makes on this subject is that integration and differentiation are almost inverse processes. So if we look at this definite integral that's on the left-hand side here, so what we're doing is we're saying I want to integrate a function from a to x. I want the definite integral from a to x of some function, and that function is going to be the derivative of f of t. Well, the first fundamental theorem told us that how can we evaluate this? Well, we can find any antiderivative for the integrand. Well, what's some antiderivative for this guy? Well, f of t is an antiderivative. So the first fundamental theorem of calculus tells us this, or right now a bit longer it says that. In other words, if we integrate a function that is itself known to be the derivative of something, or another way to say it is we differentiate a function, we integrate it using a definite integral, we get back almost the function. They're not quite inverses because we do get this minus f of a bit that is an arbitrary constant, or the specific value of f at that particular point. So that's where we can say that integration and differentiation are almost inverses of each other, but not exactly.